Every detail in this story comes from real scientific research and observation. There is a side of the moon that no human being has ever seen from Earth. Not once, not in all of recorded history. A world that has existed in complete silence for billions of years, facing away from us, always, by the laws of physics themselves. Tonight, you are going there. Welcome to Quiet Science at Bedtime. This channel tells real science stories, grounded in actual research, real missions, real data, designed to carry you gently into sleep. We're still a new channel, and if this story is the kind of thing you've been looking for, it would mean a great deal if you subscribed, hit the like button, and turned on notifications. It genuinely helps. Everything you are about to hear is based on real science. Just relax and feel free to let this play as you drift off to sleep. Now, let's begin. The moon always shows Earth the same face. This is not a coincidence. The moon rotates on its axis once every 27.3 days, the exact same time it takes to complete one orbit around the Earth. These two cycles are perfectly synchronized. The technical term for this is tidal locking. Over hundreds of millions of years, Earth's gravitational pull gradually slowed the moon's rotation until the two periods aligned precisely. Once locked, they stayed locked. The result is that the far side of the moon, the hemisphere permanently turned away from Earth, has never once been visible from our planet's surface. In October of 1959, the Soviet spacecraft Luna 3 became the first to photograph the lunar far side. The camera on board developed its own film in flight and transmitted the images back to Earth as radio signals. The pictures were blurry, difficult to interpret, but they were real. Humanity saw that hidden face for the first time. 60 years later, on January 3, 2019, China's Chang'e 4 spacecraft landed there. It was the first time any human-made object had ever touched down on the far side of the moon. The landing site was Kármán Crater, located inside the South Pole Aitken Basin, one of the largest and oldest confirmed impact structures in the entire solar system. Kármán Crater itself is approximately 186 kilometers across. That is roughly the distance from Los Angeles to San Diego, edge to edge, in a single straight line across open terrain. Tonight, you are standing inside it. The ground beneath your feet is a fine, pale gray powder. For billions of years, meteorites and micrometeorites have been striking the lunar surface in a continuous slow bombardment. Each impact shatters and melts the rock beneath, and the material cools and fractures again into ever finer particles. This accumulated layer is called lunar regolith. It covers the surface to depths of several meters, made up of particles ranging from a few micrometers to several millimeters across. It looks soft, almost like sand, but under a microscope, each grain is sharp and jagged, glass-edged fragments with no smooth curves. Because there is no atmosphere on the moon, there is no wind, no rain, no water flowing across the surface. There is no erosion in the way Earth knows it, only the slow grinding of impact after impact over billions of years. Every footstep you take leaves a clean, sharp print in the regolith, and that print will still be there, exactly as you left it, millions of years from now, unless someone comes to erase it. Look up. On the far side of the moon, Earth is not in the sky. From any point on this hemisphere, Earth sits permanently beyond the horizon, hidden behind the full bulk of the moon itself. between you and the planet you came from lies approximately 2.19 times 10 to the 10th power cubic kilometers of solid rock. That mass blocks every signal, every radio wave, every photon of reflected Earth light. Instead, there are stars. The moon has almost no atmosphere. What exists is called an exosphere, so thin it is functionally a hard vacuum by any Earth standard. Without air molecules to scatter sunlight, the sky does not turn blue during the day. It stays black. The sun itself appears as an intense, hard white point against a black background. Sunlight and stars exist in the same dark sky at the same time. And in that black sky, the stars do not twinkle. On Earth, starlight passes through layers of atmosphere at different temperatures and densities, bending and shifting constantly. That flicker is called atmospheric scintillation. On the moon, there is no atmosphere to cause it. Each star is a single, precise, unwavering point of light. The sky has looked exactly like this for billions of years. Look around the floor of von Kármán Crater. The crater rim, 186 kilometers across the basin, sits far beyond the lunar horizon, which on the moon extends only about 2.4 kilometers from where you stand due to the moon's smaller radius. The rim is invisible from the surface. What surrounds you looks like open, gently rolling terrain, scattered with smaller craters of every size. The surface is pocked with impact craters within impact craters, structures a few meters across, a few hundred meters, a few kilometers. Each one is a record of a collision. The floor of von Kármán is covered in old, dark basalt in places, overlaid with regolith. The craters here have soft, eroded rims, not sharp-edged. They are old. The slow sandblasting of micrometeorites over millions or billions of years has worn their edges down. The sun is low on the horizon, and in that low light, every small rock, every shallow depression throws a long, precise shadow across the gray surface. Von Kármán Crater sits inside the South Pole Aitken Basin, abbreviated SPA Basin, which is roughly 2,500 kilometers in diameter and about 8 kilometers deep. It formed approximately 4 billion years ago when an asteroid, perhaps several hundred kilometers across, struck the lunar surface. The energy released in that event dwarfs anything in recorded human history by many orders of magnitude. The impact likely punched through the lunar crust entirely and may have brought material from the moon's mantle closer to the surface. In 2019, the U-22 rover, deployed from Chang 4, detected minerals including olivine and low-calcium pyroxene in the regolith using its visible and near-infrared spectrometer. These minerals are thought to originate from the lower crust or mantle, exactly the kind of material scientists hope to find inside this ancient basin. The ground you are standing on may not be the moon's surface at all. It may be the moon's interior, exposed by the most violent event this world has ever experienced. Right now, it is lunar daytime. A lunar day lasts approximately 29.5 Earth days. The current day will continue for another 2 weeks before the sun sets, and when night does come, it will last 2 weeks as well. Without an atmosphere to retain heat or distribute it across the surface, temperatures swing dramatically between extremes. In full sunlight, the surface reaches around 127 degrees Celsius. In the lunar night, it drops to approximately -173 degrees Celsius. The difference between day and night on the moon is 300 degrees. The line that separates them, the terminator, moves slowly across the surface, about quints kilometers per day. Right now, on the far side of that line, the land is in complete darkness. But here in Kármán Crater, the sun is still up. Everything around you is completely silent. And silence here means something different than it does on Earth. Sound is a pressure wave, a mechanical disturbance that propagates through a medium. On Earth, that medium is air. On the moon, there is no medium. There is nothing for pressure waves to travel through. No explosion, no impact, no vibration can reach your ears as sound. If a meteorite struck the surface 10 meters away from you right now, you would not hear it. You would only feel the faint vibration through the ground beneath your feet. This silence is billions of years old. Since the moon solidified, since its surface took the shape it has today, this silence has never once been broken. There is another layer to the isolation of the far side. The moon itself blocks all direct communication with Earth. Radio waves cannot pass through solid rock. From the far side, there is no line of sight to our planet. This means that before Chang 4 could land here, the problem of communication had to be solved, because there is no way to send or receive signals between this surface and Earth without a relay. China's National Space Administration launched a solution 7 months before the lander, a relay satellite called Kechao, which means magpie bridge, a reference to a Chinese legend in which a bridge of birds connects two separated lovers across the sky. Kechao was placed in a halo orbit around the Earth-Moon Lagrange point 2, known as L2. This is a gravitational equilibrium point located approximately 65,000 kilometers beyond the moon on the far side. At this position, the gravitational pull of Earth, the gravitational pull of the moon, and the centrifugal force of the orbital motion all balance in a way that allows a spacecraft to maintain a relatively stable position. From L2, Kechao has a continuous line of sight to both the lunar far side and to Earth. Every signal that Chang 4 transmits travels first to Kechao, and from there across 384,400 kilometers to Earth. That signal travels at the speed of light. It takes approximately 1.28 seconds one way. On January 3, 2019, when Chang 4 descended into this crater, it did so entirely on its own. There was no possibility of real-time guidance from Earth. The signal delay alone made it impractical, and the indirect relay through Kechao added another layer of complexity. The lander's onboard guidance computer managed the entire descent autonomously, calculating altitude, adjusting velocity, analyzing terrain in real time with cameras, and selecting the final touchdown point. If the computer detected an obstacle, it moved the target. The spacecraft made those decisions alone, in the dark, in a place humans had never sent anything before. The landing happened here, in this silence, without an audience. Chang 4 is still in this crater. The lander monitors surface temperature, neutron radiation, and low-frequency radio waves. The Untouched rover has been moving slowly across the regolith since shortly after landing, photographing terrain, scanning for minerals with its spectrometer, and mapping the subsurface structure with ground-penetrating radar. U-22 weighs approximately 140 kilograms, 6 wheels, solar panels folded outward. The Lunar Penetrating Radar System (LPR) emits pulses of radio energy into the surface and records the reflections to map layered structures tens of meters underground. What the radar found confirmed something important. Below the surface of von Kármán Crater are multiple distinct stratigraphic layers, distinct bands of material at different depths. The uppermost layer is fine regolith. Below that, slightly coarser ejecta. Below that, denser material mixed with impact debris from multiple overlapping events. Each layer represents a different period in the crater's history, a different impact, a different era. The moon's surface is a geological archive. Each layer is a page. U-22 was originally planned to operate for 3 months, but it continued far longer, surviving repeated lunar nights by entering a hibernation mode, powering down to weather temperatures of -173 degrees Celsius, and waking again when the sun returned. Each lunar day, approximately 15 Earth days of sunlight. Each lunar night, 15 Earth days of cold. The rover followed that rhythm, sleeping and waking, over many cycles. Its wheel tracks are pressed into the regolith. They will remain there undisturbed for millions of years. The far side of the moon has a thicker crust than the near side. The near side averages approximately 30 to 40 kilometers of crustal thickness. The far side averages 60 to 80 kilometers, nearly double. The reason for this asymmetry is not fully understood, and multiple hypotheses have been proposed. One leading idea involves the thermal history of early moon formation. Shortly after the moon formed, the hemisphere facing Earth would have been exposed to more radiated heat from the young, hot planet. That added warmth may have slowed the cooling and solidification of the near side crust, allowing it to remain thinner. The far side, cooling faster, built up a thicker shell. A second hypothesis involves a second moon. Early in the solar system's history, a smaller companion body may have been orbiting the Earth-Moon system alongside the moon, and eventually collided with the far side at low velocity, piling up crustal material and thickening that hemisphere permanently. Neither hypothesis has been definitively confirmed. What is confirmed is the asymmetry itself, and one of its consequences. The far side has almost no volcanic plains. The near side of the moon is covered in large, dark, flat regions called maria, the plural of mare meaning sea. These are ancient basaltic lava plains formed when magma from the moon's interior erupted through the thin near-side crust billions of years ago. The dark patches you see when you look at the full moon from Earth, those are the maria. They cover about 31% of the near side. The far side has almost none of them. Less than 3% of the far side is covered in mare. The rest is ancient, heavily cratered highland terrain, some of the oldest exposed surface in the solar system. The far side of the moon is the oldest face it has. You are standing at the bottom of one of the deepest confirmed impact structures in the solar system. The crust beneath you is thinner here than most of the far side, compressed and fractured by the original South Pole Aitken impact 4 billion years ago. Beneath the crust lies the mantle. Beneath the mantle, the core. The moon's core is estimated to have a radius of only about 240 to 300 kilometers, roughly 20% of the moon's total radius. Unlike Earth's core, the moon's is largely solid and generates no significant global magnetic field. Because the moon has no magnetic field, the solar wind, a constant stream of charged particles flowing outward from the sun, strikes the lunar surface directly. Earth's magnetosphere deflects most of that stream before it reaches us. Here, there is nothing to stop it. Over billions of years, solar wind has implanted hydrogen ions deep into the crystalline structure of regolith grains across the entire lunar surface. The dust beneath your feet carries atoms from the sun. The far side of the moon is the most electromagnetically quiet place accessible to humanity. Every radio signal generated on Earth, television broadcasts, mobile phone transmissions, air traffic communications, radar systems, satellite uplinks, all of it is blocked by the moon's bulk. The rock between you and Earth is an impenetrable shield, more effective than any technology humans have ever built. Modern Earth is saturated in electromagnetic noise. Radio telescopes on Earth's surface must cope with constant interference from human civilization. Even in the most remote locations, signals bleed through. Sensitive instruments designed to detect faint cosmic signals have to filter out layers of man-made noise that were never there a century ago. On the far side of the moon, none of that noise exists. This is why scientists have been dreaming of placing a radio telescope on the lunar far side for decades. From that location, it would be possible to observe radio frequencies below 30 megahertz, extremely low frequency radio waves that are completely invisible from Earth. Our planet's ionosphere, the layer of ionized gas in the upper atmosphere, absorbs and reflects radio waves in this frequency range before they can reach the ground. No ground-based telescope has ever seen the universe at these frequencies. But there is something that emits at those frequencies. The early universe. In the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas, and it was dark. Before the first stars ignited, before any galaxies formed, hydrogen atoms were distributed across the cosmos in vast, cold, slowly clumping clouds. These atoms emitted and absorbed radiation at a very specific wavelength, 21 centimeters. But because the universe has been expanding ever since, those signals have been stretched. What was emitted at 21 centimeters has been redshifted down into the low-frequency radio range, below 100 megahertz, often below 30 megahertz. This signal from the cosmic dawn has never been detected. Earth's ionosphere blocks it. Terrestrial interference drowns it. Existing space-based telescopes were not designed for it. A radio telescope on the lunar far side, shielded from all human-made electromagnetic noise, positioned beneath a sky that has been radio quiet since before the Earth itself formed, would be the most powerful tool humanity has ever built for listening to the early universe. That telescope does not yet exist, but you are standing in the place where it might someday be built. You begin to walk. Slowly, each step feels lighter than you expect. The moon's gravitational acceleration at the surface is approximately 1.62 meters per second squared, about 16.6% of Earth's. A person weighing 160 pounds on Earth would weigh roughly 26 pounds here. Walking feels effortless and strange at the same time. Each footfall carries you slightly farther forward than your muscles intended. Apollo 15 astronaut David Scott described moving across the lunar surface as similar to slow jogging. You have to consciously hold yourself back to avoid bounding forward with each step. With each step, a faint puff of regolith lifts away from the surface. But without air, the particles don't drift or blow. They follow ballistic arcs, rising briefly, then falling back down in perfect silence. The fine dust catches the low sunlight as it rises, briefly holding a faint glint before settling again. It happens with every step. A small, quiet flash of light, then stillness. You stop. There is a small impact crater in front of you, perhaps 50 meters across. Its rim is soft and low, rounded by time. This is what age looks like on the moon, not the sharp bowl of a fresh impact, but a gentle depression worn down by millions of years of micrometeorite rain. On Earth, wind and water would fill and erase a crater this size in thousands of years. Here it has persisted for perhaps hundreds of millions of years, slowly softening at the edges, never disappearing entirely. You stand at its rim and look down into it. The floor is flat with regolith. The walls slope inward gently. There is no color, only gray. Pale gray at the surface, slightly darker in the shadows. The moon is a world of gray. The dominant minerals in lunar regolith are plagioclase feldspar and pyroxene, both of which produce shades of gray to pale brown. The dark Maria regions have more iron-rich basalt, which reads darker from a distance. The highlands, like where you are standing, are brighter, reflecting more sunlight because of the higher plagioclase content in the ancient crustal rock. 382 kilograms. That is the total weight of lunar material returned to Earth by all 6 Apollo landings combined. Those samples are stored primarily at the Johnson Space Center in Houston, where they are maintained in a controlled nitrogen environment to prevent contamination. They have been studied for over 50 years, and they still yield new scientific findings. In June of 2024, Chang'e 6 became the first mission to retrieve samples specifically from the lunar far side. It landed inside the South Pole, Aitken Basin, the same ancient impact structure you are standing in now, and returned approximately 1.9 kilograms of material to Earth. For the first time in history, scientists held far-side regolith in their hands. The analysis of those samples is still ongoing, but the ground beneath your feet stretches across thousands of square kilometers. What Chang'e 6 returned was a single small handful from a single point. Nearly all of this surface remains untouched. Chang'e 4 carried a small biology experiment called the lunar microecosystem, a sealed metal canister roughly the size of a coffee can. Inside were seeds of cotton, rapeseed, and potato, along with fruit fly eggs, yeast, and small amounts of water, air, and a miniature camera. The experiment was designed to test whether plant germination was possible under lunar surface conditions, low gravity, ambient radiation, and whatever temperature regulation the canister itself could provide. On January 7, 2019, just 4 days after landing, a cotton seedling sprouted. It grew for the duration of that first lunar day. Then the lunar night arrived. Temperatures inside the canister plunged, and the seedling died. The outcome was expected. The canister had no active heating system to survive the 2-week lunar night. But for a few days, inside this crater, on the far side of the moon, something grew. For the first time in the history of this world, a living thing opened its leaves here. In silence, without ceremony, in the same silence this place has held for 4 billion years. You continue walking, one step at a time across the gray floor of the crater. The Chang'e 4 lander is visible in the distance, its landing legs spread across the surface, its solar panels angled toward the sun. Around its base, the retrofire engines scattered regolith during the final descent, leaving a subtle radial pattern pressed into the surface. That pattern will not erode. The dust around it will not be disturbed by wind. Centuries from now, the pattern will still be exactly as it was the moment the engines cut off. The lander carries instruments from 4 countries: China, Germany, Sweden, and Saudi Arabia. Germany's Kiel University developed the LND, the Lunar Lander Neutrons, and dosimetry instrument. It measures the radiation environment at the lunar surface, cosmic rays streaming in from deep space, and secondary particles produced when those rays strike the lunar rock. Its findings provide data essential for planning future crewed lunar missions. The radiation levels at the lunar surface are approximately 200 to 1,000 times higher than what humans experience on Earth's surface, a direct measure of how effectively Earth's magnetic field and atmosphere shield us from space. Sweden's KTH Royal Institute of Technology contributed the ASAN instrument, the Advanced Small Analyzer for Neutrals, which observes neutral atoms produced when solar wind particles interact with the lunar surface. It helps characterize how the sun's particle stream physically transforms the regolith over time. All of this measurement is happening quietly, here, in this crater. No alarms, no announcements, data moving upward to Queka, and from there across space to Earth. The science is patient. It simply continues. No human being has ever stood on the far side of the moon, but 3 humans have seen it from above. In December of 1968, Apollo 8 carried Frank Borman, Jim Lovell, and William Anders into lunar orbit, the first crewed spacecraft ever to leave Earth orbit. As they passed around the far side, communications with Earth went silent. The moon's mass blocked the signal completely. For roughly 45 minutes per orbit, the 3 astronauts were more isolated from humanity than any human beings had ever been. What they saw from that altitude was a landscape of craters. Unbroken, overlapping, ancient craters as far as their windows could show. No dark Maria, no smooth basalt plains, just the relentless churned highlands of the oldest surface in the solar system. Jim Lovell later described it as looking like a gray sandbox that a construction crew had left unfinished. You are inside that sandbox right now. You crouch down and press your palm flat against the regolith. The particles shift under your hand. They conform to the shape of your fingers. Each grain is too small to feel individually. Together they feel like very fine, dry powder. Some of the grains cling, not from moisture because there is none, but from the electrostatic charge each particle carries, acquired through billions of years of exposure to solar radiation and the solar wind. The finest dust is nearly impossible to shake loose once it makes contact. Lift a small handful. In the moon's weak gravity, it weighs almost nothing. You open your fingers slowly, and the particles fall, all of them at almost exactly the same rate, regardless of size. This is something Galileo predicted in the late 16th century. He argued, against the prevailing belief of his time, that all objects fall at the same rate regardless of their mass, and that differences in fall time on Earth were caused by air resistance alone. In April 1971, Apollo 15 Commander David Scott performed a demonstration on this exact point. He held a geological hammer in one hand and a falcon feather in the other, extended both to shoulder height, and released them simultaneously. In front of a rolling camera, both struck the surface at the same moment. The regolith falls from your hand. All of it, together, at the same rate. The moon is full of things like this, simple, clean confirmations of physics that Earth's messy, air-filled environment obscures. You look at what remains on your palm. Some of these grains are not irregular fragments. Some are tiny spheres, nearly perfect glass beads, a fraction of a millimeter across. These are called agglutinates. They form when micrometeorites strike the surface at high velocity, briefly melting and splashing the surrounding regolith. Some of that molten material is flung upward in microscopic droplets that cool instantly in the vacuum, solidifying into glass spheres before they fall back to the surface. In heavily worked regolith, agglutinates can make up 40 to 50% of the total volume. You are holding billions of years of micrometeorite history in your hand. You let it fall. You stand back up and look out across the crater floor. Imagine for a moment what this place might look like 100 years from now. Perhaps there will be a structure here, a low, wide framework of antenna elements spread across several kilometers of the crater floor, a radio telescope unlike anything that exists on Earth. Each antenna element would be simple, a wire dipole laid flat on the regolith, connected by cable to a central processing unit buried in the rock. No moving parts, no tracking mechanism. The whole array would listen passively, pointed at the sky, absorbing the faint signals that have been traveling toward this world for billions of years. In the frequency ranges that no instrument on Earth has ever heard. The signals from the first hydrogen atoms, the first structure of the early universe, the universe as it was before a single star existed. The far side of the moon is the only place in the known solar system from which that listening would be possible. Whether any of that will happen, no one can say, but the silence is already here. The electromagnetic quiet is already here. The crater floor is already flat and wide and waiting. The physics that makes this place unique has been in place for 4 billion years. The moon's future is also in motion. Each year, the moon drifts approximately 3.8 centimeters farther from Earth. The mechanism is tidal friction. The moon's gravity raises tidal bulges in Earth's oceans. As Earth rotates faster than the moon orbits, those bulges are always slightly ahead of the moon's position. Their gravitational pull transfers rotational energy from Earth to the moon, gradually pushing the moon into a slightly wider orbit. Slowly, steadily, every year 3.8 centimeters. Over hundreds of millions of years, the moon will be noticeably farther away. Total solar eclipses, which are possible only because the moon and sun currently appear almost exactly the same size in Earth's sky, will eventually no longer be possible. The moon will be too small in the sky to cover the sun completely. But right now, the moon is here. You are on it. You walk to a low, flat section of the surface and stop. The sun is still up, still low on the horizon, still drawing long shadows from every small stone and gentle rise. The light here is harsh and high contrast. Surfaces in direct sunlight are blazing white, shadows are absolute black, and there is no atmospheric softening of the transition between them. No haze, no diffusion, every edge is exact. Your own shadow stretches out behind you on the regolith. Sharp-edged, precise, perfectly still. You look out across the surface of von Kármán Crater. Billions of years of collision, billions of years of silence, billions of years of this exact same sky. You are standing in a place that has been waiting, patiently, for 4 billion years. And now, briefly, something is here. You sit down on a low, flat rock near the crater floor. It is not a dramatic rock, just a fragment, maybe half a meter across, resting on the surface at a slight angle, probably ejecta from a smaller impact nearby, thrown here and settled thousands or millions of years ago. It has been sitting in exactly this position ever since. No force has moved it, no weather has worn it. The sun has bleached the side that faces upward, the underside in permanent shadow, since the day it landed is a few degrees cooler. You rest your hand on its surface. The rock is basalt, dark, fine-grained, formed when ancient lava cooled quickly. The moon was once volcanically active. Between roughly 4 billion and 1 billion years ago, magma from the interior pushed upward through fractures in the crust and poured out across the surface. On the near side, those eruptions were extensive. They filled the great impact basins and formed the dark maria you can see from Earth with the naked eye. Here on the far side, the thick crust suppressed most of that activity, but not all of it. Some of the lava that did reach the surface did something else as well. As lava flows move across a landscape, the outer surface of the flow cools and hardens first, forming a solid crust while the molten rock inside continues to move. When the eruption eventually slows or stops, the lava drains from beneath the hardened crust, leaving behind an empty tunnel, a lava tube. On Earth, lava tubes exist in Hawaii, in the Canary Islands, in Iceland. They are impressive structures, sometimes tens of meters wide, sometimes kilometers long, but the moon's lower gravity changes the physics dramatically. Lower gravity means lower pressure on the walls and ceiling of a lava tube as it forms. This allows lunar lava tubes to grow far larger than anything possible on Earth. Theoretical modeling and radar data suggest that some lunar lava tubes could be hundreds of meters wide, large enough to contain a city. Somewhere beneath this surface, there may be caverns that no instrument has fully mapped and no eye has ever seen. The rock beneath your hand has been sitting in this exact position for longer than the Rocky Mountains have existed. The Rockies formed roughly 80 million years ago, pushed upward by tectonic plate movement. This fragment of basalt on the far side of the moon was already old before those mountains existed. It will still be here long after those mountains have been worn flat by erosion. You set your hand down and look upward. The Milky Way arcs overhead. Without atmospheric scattering, the structure of the galaxy is fully visible from edge to edge. The core, a dense, luminous band of stars toward the constellation Sagittarius, glows with a brightness that no human eye on Earth's surface in any era has ever seen it. On Earth, even in the darkest skies, the atmosphere absorbs and scatters a portion of that light. Here, nothing is absorbed. The full optical output of 100 billion stars, unfiltered, reaches your eyes. At the center of that glow, 26,000 light-years away, is a supermassive black hole. Sagittarius A star, mass approximately 4 million times that of the Sun. It is not currently active in the way that quasars are active. It is not consuming large amounts of material or generating the enormous jets of energy that some galactic centers produce. It sits relatively quietly, bending space-time around itself, pulling stars into tight orbits that take years to decades to complete. The closest known star to Sagittarius A star completes a full orbit every 16 years, reaching speeds of nearly 8,000 kilometers per second at its closest approach. That black hole has been there for billions of years. The galaxy has been rotating around it for billions of years. And this crater has been here for almost as long, turning slowly with the moon, riding the moon's orbit around the Earth, riding the Earth's orbit around the sun, riding the sun's orbit around the galactic center, making the long journey around that central mass once every 225 million years. In the 3.9 billion years this crater has existed, the solar system has completed roughly 17 full orbits of the Milky Way. There is something else the moon does that most people never think about. It stabilizes the Earth. Earth's axial tilt, the angle at which our planet leans relative to its orbital plane, is currently about 23.4 degrees. This tilt is what creates the seasons. Without it, there would be no summer, no winter. The equator would always receive more sunlight than the poles, and the temperature difference between latitudes would be far less dramatic. But without the moon's gravitational influence, that tilt would not stay stable. Computer simulations suggest that without the moon, Earth's axial tilt could wander chaotically over millions of years, swinging from near zero to as high as 85 degrees. A tilt of 85 degrees would mean the poles pointing nearly directly at the sun at certain times of year. The climate consequences would be extreme. Ice ages and heat events would be far more severe and far less predictable than anything in Earth's geological record. The moon acts as a gravitational anchor, damping those variations and keeping Earth's tilt within a relatively narrow range over geological time. The same moon you are standing on right now has been quietly doing that for 4.5 billion years. While this crater sat in silence on the far side, the moon was keeping the other side of the planet stable enough for life to develop in something resembling continuity. Somewhere between science and imagination, you find yourself thinking about the first human being who will stand where you are standing now. They don't exist yet. There is no mission currently scheduled to land a person on the far side. The communication relay infrastructure isn't in place. The surface hasn't been mapped in enough resolution. The life support requirements for the far side's prolonged isolation haven't been fully solved, but the plans are being discussed. The studies are being written. Whenever that person comes, and it may be decades from now, this is what they will see. This gray floor, these craters within craters, this absolute black sky with its unwavering stars, the sun sitting low on the horizon, throwing shadows that are impossibly sharp, the silence so total that the only sound will be the sound of their own breathing inside a helmet. They will take one step, and the regolith will compress under their boot in exactly the same way it compressed under yours tonight. They will leave a print, and that print, and your print, and the tracks left by you 26 wheels will all be there together on the same crater floor, records of different moments, different arrivals, all preserved in the same unchanging dust. The moon keeps everything it is given. You stand up slowly. The rock you were sitting on stays exactly where it was. It will be there when the first astronaut arrives. It will be there long after the last one has left. The surface of von Kármán Crater in the low afternoon light has a quality that is difficult to describe and almost impossible to photograph accurately. Every small feature, every pebble, every crater rim, every ripple in the regolith casts a shadow in one direction only. All the shadows fall the same way, parallel to each other, because the sun is a single point source in a sky with no diffusion. The result is a landscape that looks simultaneously flat and deeply three-dimensional, a landscape that seems both lifeless and strangely present. You have been here for a while now. The Terminator is still far away. The sun has moved almost imperceptibly since you arrived. By any lunar measure, almost no time has passed at all. But by Earth time, by the measure of heartbeats and breaths, and the small, steady rhythm of a body at rest, time has been passing quietly. Let it pass. There is no appointment, no signal waiting to be answered, no clock whose alarm is set. Just the crater, just the stars, just the silence that has been here since before any of the words for silence existed. Your steps begin to slow. There is no urgency here. The lunar day still has days left in it. The sun will continue its slow arc across the black sky. The Terminator will continue its 15-kilometer-per-day crawl, and the stars above you will not move, not on any time scale you would notice standing here. You stop walking. You just stand. The regolith is beneath your feet. The black sky is above you. The silence is everywhere. Look at the stars. The nearest star to Earth, other than the Sun, is Proxima Centauri. It sits approximately 4.24 light-years away. The light arriving in your eyes from that star right now left its surface more than 4 years ago. It has been traveling through space at 299,792 kilometers per second for over 4 years to reach this moment. Sirius, the brightest star in Earth's night sky, is approximately 8.6 light-years away. That light left 8.6 years ago. Betelgeuse, the red supergiant in the constellation Orion, is approximately 700 light-years away. The light you are seeing now left that star 700 years ago, when medieval cathedrals were still being built in Europe, when the Mongol Empire was at the peak of its reach. Rigel, also in Orion, sits roughly 860 light-years away. Its light has been traveling since before the Black Death swept across the known world. The sky above you is not one moment in time. It is thousands of moments, arriving simultaneously. When you look up, you are seeing light from different centuries, different millennia, all reaching you at once. Some of these photons have been traveling longer than human civilization has existed. Some have been traveling longer than our species has existed. And farther still, the Andromeda Galaxy, M31, the nearest major galaxy to our own, sits approximately 2.5 million light-years away. Its light has been traveling since before Homo sapiens existed, since before Homo erectus walked across the African savanna, since before the genus Homo existed at all. All of that light is landing on this crater floor right now. You sit down on the regolith. Slowly, you lower yourself. The moon's low gravity makes the movement easy, almost effortless. The regolith shifts slightly as your weight settles into it. You place your palms flat on the surface on either side of you. The particles press between your fingers. This material beneath your hands, it formed during the moon's earliest history, more than 4 billion years ago, when the lunar magma ocean cooled and solidified. The plagioclase feldspar crystallized and floated upward, buoyant in the molten rock, forming the first solid crust. That crust was then broken, melted, reformed, and broken again by billions of years of impacts. What you are touching now is the accumulated debris of that entire history. The moon formed from Earth. Approximately 4.5 billion years ago, a Mars-sized object called Theia collided with the early Earth. The impact was not a direct hit, more of a glancing blow. Enormous amounts of mantle material from both Earth and the impactor were ejected into orbit. Over thousands of years, that debris coalesced under gravity into what became the Moon. One of the strongest pieces of evidence for this hypothesis is the oxygen isotope ratio of lunar rocks. The proportion of oxygen-16, oxygen-17, and oxygen-18 in lunar samples is nearly identical to Earth's mantle composition. The two bodies formed from the same material. In a very deep sense, what you are sitting on is a piece of Earth, ejected, shaped, cooled into something new. Let your breathing settle. The sun is low, the shadows are long and sharp, the stars are fixed and still in the black sky above you. The regolith is under your palms. The silence of the lunar far side holds everything. Lunar time moves slowly. The terminator creeps at 15 kilometers per day. The regolith changes by micrometers over millennia. The crater rim erodes by fractions of a millimeter per million years. Nothing here is in a hurry. The geological processes that shaped this landscape operated over timescales that have no equivalent in human experience. Von Kármán Crater is approximately 3.9 billion years old. In those 3.9 billion years, the first single-celled life appeared on Earth, then multicellular life, then the Cambrian explosion, which produced most of the animal body plans that exist today, then fish, then amphibians, then reptiles, then dinosaurs, who existed for approximately 165 million years before an asteroid ended the age of non-avian dinosaurs 66 million years ago. Then mammals diversified, then primates, then perhaps 300,000 years ago, modern humans. All of that happened while this crater sat here, unchanged in its essential form. The entire history of life on Earth fits inside the existence of this single impact crater. Close your eyes if you want to. The crater is still there. The stars are still there. The silence is still there. Nothing needs to change. Let the rhythm of your breathing slow. Let the surface hold you. You lie back on the regolith. The moon's low gravity settles you gently into the surface. The particles shift and conform around you. Your weight, only a fraction of what it would be on Earth, presses into the ancient dust. Above you, the black sky. Above you, the stars, unwavering, permanent, spread across the full width of that blackness from one horizon to the other. No atmosphere to soften them, no city lights to drown them out, no clouds to hide them, just the raw, unfiltered universe directly overhead. You are on the far side of the moon, approximately 384,400 kilometers from Earth, though that distance changes continuously as the moon traces its elliptical orbit. At its closest, the moon comes within roughly 360,000 kilometers of Earth. At its farthest, it reaches about 405,000 kilometers. Right now, you are somewhere along that arc, moving at approximately 1.022 kilometers per second in relation to Earth. The moon is in motion. Everything is in motion. The moon orbiting Earth, Earth orbiting the sun orbiting the center of the Milky Way at roughly 220 kilometers per second, completing one full galactic orbit approximately every 225 million years. The Milky Way itself moving through the local group of galaxies, being drawn toward the Virgo supercluster, which is itself part of the larger structure called Laniakea, a supercluster spanning approximately 500 million light-years. Everything is moving, and yet here, from the surface, nothing seems to move at all. The stars hold their positions. The crater floor is still. The silence does not waver. In a universe of constant motion, this surface is one of the most still places you could ever be. Your back is against regolith that has not been touched in 4 billion years. The sky above you has looked like this for 4 billion years. The South Pole, Aitken Basin stretches thousands of kilometers in every direction. Von Kármán Crater holds you at its center. The moon's orbital period around Earth is 27.3 days. That means a single lunar orbit, the circle you are riding right now, takes just over 4 weeks. As the moon moves along that orbit, Earth slowly rises and sets over the near-side horizon. But here, on the far side, Earth never appears. It is always behind you, always below the horizon, always on the other side of the moon. You have never been this far from everything. In the whole of your life on Earth, every moment was surrounded by the products of civilization, electricity, air, sound, signal. Here, none of those things reach. The rock beneath you has been here since before the first life formed in Earth's oceans. The silence around you has not been touched. But it is not a frightening silence. It is simply what the universe is like when there is nothing to disturb it. The sun continues its slow traverse across the black sky. The shadows on the crater floor shift by fractions of a degree. The Terminator, still weeks away, continues its patient crawl. There is no rush. There has never been a rush here. The stars above you were burning before the Earth formed. Many of them are still burning. Some of the light reaching you right now left those stars before the moon existed. It traveled across the void through the forming solar system, past planets and asteroids and comets, across 384,400 kilometers of empty space, and it has arrived here, at this exact point on the lunar surface, at this exact moment, right where you are. The universe is full of arrivals like this, quiet, precise, unobserved. You do not need to hold anything. Let it all simply be there. The regolith beneath you, the black sky above you, the stars that do not flicker, the silence that has no bottom, the crater that was old before life began. Let them hold you. You don't need to do anything else. The lunar day continues. You are here. That is enough. Thank you for spending tonight here on the far side of the moon. Quiet Science at Bedtime tells real science stories, built on real research, real missions, real data, designed to carry you gently into sleep. In the episodes ahead, we'll travel to the rings of Saturn, the canyon systems of Mars, the storms of Jupiter, and much further beyond. If tonight felt like something worth coming back to, please subscribe, leave a like, and turn on notifications. Every one of those things genuinely helps this channel grow. Sleep well. Good night.